In this module, we want to develop some intuition about lattice vibrations in solids without using too much mathematics. And so let's start with the simplest possible case of a diatomic molecule, which will eventually extend to a periodic solid. So we'll take a molecule with two atoms, each of mass m, and joined by a chemical bond, which we'll sketch like a little spring. And these atoms have some equilibrium spacing, which we'll call x0. So their bond length when their minimum energy is x0. And we know that if we stretch this bond by some small amount delta x, say, so that this distance is now x0 plus delta x, then there'll be a force on the atoms that tends to want to bring them back to their equilibrium spacing, back to x0. So this force is acting to pull the atoms back to their equilibrium distance. And likewise, if we compress our molecule by some small amount, so that now the size is the original bond length minus delta x, then there'll be a force on these atoms acting outwards in order to try to restore the equilibrium bond length. And we know that as long as we don't stretch or compress the atom by too much, that this force, which we've called F, is linear in x. It's negative because when we increase the bond length, it acts to decrease it again, and vice versa. And we usually call the proportionality constant K. And this, of course, is familiar to us in classical physics as Hooke's law. Alternatively, if we prefer to think in terms of energy instead of in terms of forces, we can plot the energy as a function of the bond length and that energy will be a minimum at x0, and if the force is linear in x, the energy will change quadratically. It's supposed to be even around x0. And sorry, I should have written up here delta x, and my energy E is a half times K, same K as in the expression for the force, times delta x squared, where delta x is the change in the bond length from the equilibrium bond length x0. So we see that our energy, our potential energy is harmonic, and we know that our molecule will behave like a harmonic oscillator. So let's look at the behavior of this molecule first classically. So if we solve Newton's laws, just F is equal to ma, we obtain a value for the frequency of vibration, which is given by the square root of the force constant divided by the reduced mass, where the reduced mass in this case, or in general, is the product of the masses divided by the sum of the masses, which in this case is just m over 2, because both of our masses are equal. If you want to see the derivation of that, you can do it yourselves or find it in any basic mechanics book. Let's go one step further and write down what happens if we solve the Schrödinger equation. So if we instead obtain the quantum mechanical solution, with our potential energy equal to the harmonic energy that we just sketched of k delta x squared, then we find that our energy is quantized with the energy of the nth energy level being given by n plus a half times h bar omega, where omega is the same value as in the classical case, the square root of k over mu, and n can take any integer. This is the familiar solution to the quantum harmonic oscillator problem. Okay. So that's just for a diatomic molecule. Now we want to extend to the case of a periodic solid and see in particular how these frequencies are modified by the fact that the solid is periodic rather than an isolated molecule. So let's now make a periodic solid. And to make a simple example, I've just made a one-dimensional chain of the molecule that we just looked at. So now we have a unit cell, which looks like this. And each unit cell is containing one molecule. It continues in both directions. And let's say that the size of the unit cell is A, say. And of course, our molecules are not isolated now, they're connected to each other. So really I should draw my springs, my bonds between my atoms also between the other atoms. So we want to think about how is the vibration of the isolated molecule modified by the fact it now has these neighbors. So let's start at the case for the wave vector q, which is equal to 0. For some reason, the wave vector in the case of phonons is usually called q. This is the quantity that in the case of electrons is usually called k, but we'll stick to the convention and call it q. So q is the center of the Brillouin zone, and what that means is that every unit cell has an identical vibration. So let's just sketch two of our unit cells. So what that means is that if in the first unit cell the atoms are vibrating at some moment in time, they're vibrating in the outwards direction, that means that in the second unit cell, they're doing exactly the same thing. And this you can imagine just by thinking about the forces that this will have between the atoms is a rather high energy, high frequency lattice vibration. These two atoms here are really getting in each other's way, or another way to think of it is as this bond length, as this bond is being elongated, I have to pay an energy, a half K times the change in bond length here. This bond is getting squashed, so I have to pay an energy of half K times the change in bond length squared here, and so on. So this lattice vibration is going to be rather high energy, which is the same as saying high frequency. So we'd expect in our periodic solid that this particular form of lattice vibration would have a rather high frequency at Q is equal to 0. If we go to the boundary of the Brillouin zone, the wave vector is equal to pi over a, we know that this means that neighboring unit cells are out of phase with each other. So again, let's just make a cartoon of what this looks like for this particular lattice vibration. Here are two unit cells. That means that at the moment in time when my first unit cell is vibrating so the atoms are moving outwards, my second unit cell is vibrating so that the atoms are moving inwards. And in this case, you can see that these two atoms in the middle are not stretched or compressed. And so this will be a lower frequency vibration. It'll be less, it'll take less energy to make this vibration. So I can immediately, just from this simple analysis, sketch the frequency as a function of Q between Q is equal to 0 and Q is equal to pi over A. And I know that my frequency at Q is equal to 0 is going to be higher in energy than my frequency at Q is equal to pi over A. So just from this simple cartoon argument, I can see that the frequency is going to be highest at the center of the Brillouin zone, and Q is equal to 0, and it'll come down in energy as I move towards the Brillouin zone boundary. Okay. Now, there's another vibration in this one-dimensional solid in which both atoms in the unit cell move in the same direction. We looked in this first example at the atoms in the unit cell moving in opposite directions, and there's a second possible vibration in which they both move in the same direction. So let's call this vibration 1. Atoms in the unit cell move in the same direction. Sorry, move in the opposite direction. And now we're going to look at vibration 2, second vibration, in which the atoms in the unit cell move in the same direction. And again, let's start at Q is equal to 0. And just for simplicity, we'll look at just 2 unit cells. So within the unit cell, our atoms are moving in the same direction. We're at Q is equal to 0. And so all of the unit cells are doing exactly the same thing. And we see that this particular pattern of atomic displacements is actually not a vibration at all. This is just a translation of the lattice, and this has a frequency of 0. So we can add another point to our plot, which is that at Q is equal to 0, the frequency of this particular pattern of atomic displacements has a value of 0. It's not actually a vibration at all, it's the translation of the lattice. Now let's go to wave vector Q is equal to pi over A, in which our neighboring atoms, our neighboring unit cells, are out of phase with each other. But again, we take the case of within the unit cell, the atoms are moving in the same direction. And just to help us visualize, I'm going to draw one more unit cell here because it's a little hard to see with just 2. So my third unit cell is the same as the first. And this situation should actually remind us of what we saw previously at K is equal to pi over A, in the case when the atoms in the unit cell were moving in opposite directions. We have pairs of atoms that are moving against each other, and then pairs that are not stretched or compressed. So here we have this pair of atoms that's being stretched, this pair that's not stretched or compressed, this pair that's stretched, and this pair that's not stretched or compressed. And so this is a vibration. And in fact, its frequency is the same as for vibration number 1 at Q is equal to pi over A. So we have, for our second branch, I'm going to draw it in a different color. actually evolves like this. And importantly, at q is equal to pi over a, the frequencies of both of these branches are the same, at least in the case when the two atoms are identical, or only in the case when the two atoms are identical. So what we want to look at next is, what if the atoms are different? And an example of atoms that are different might be a chain of positive and negative ions. So there are two aspects that are important here. First is that at q is equal to 0, the high frequency mode that's vibration 1, we called it, in which the ions were vibrating against each other. Let's sketch. Has an electric dipole, has an oscillating electric dipole. We can see that in each case, as a function of time, the plus and minus ions move further apart or closer together, and so the electric dipole associated with them varies with time. It oscillates harmonically with time. And this means that it couples to light this lattice vibration can be activated using electromagnetic radiation. And so we call it, it gets a name because of this, an optical phonon. In 3 dimensions, these optical phonons are further classified as either longitudinal we call the longitudinal optical or the LO phonon, or transverse TO phonon, transverse optical phonon, depending on whether their vibrations are either along or perpendicular to the wave vector, respectively. I'm going to go back a page and add this label to our plot. This guy up here is our optical phonon. And even though the light, of course, only can cause an excitation at Q is equal to 0, we refer to the entire branch as the optical phonon branch. The other phonon has a name too, and it's called the acoustic phonon. And the reason for that is that sound propagates with such a displacement pattern, and yeah, because sound is propagating in this way, it's called acoustic. Okay, so let's go back to our list then of differences when the atoms are different. So the first one is this oscillating electric dipole associated with the fact that the lattice vibration has two different ions. The second difference in behavior when the two atoms are different is that the two branches which we called either vibration 1 and vibration 2, or the optical, we now have official names for them, the optical and the acoustic branches, which previously at Q is equal to pi over A had the same energy, no longer have the same energy. And I think this is a little bit hard to see from the cartoons that we sketched of the atoms oscillating. But if you work through the mathematics, it drops straight out of the math and one can see it very obviously. So in the case where the two atoms are different, our omega versus Q plot from Q is equal to 0 to Q is equal to pi over A. It's the optical branch looking like this, and the acoustic branch then no longer meets with the optical branch. And we have a splitting here in the frequency when the atoms are different. Okay, so this discussion so far, we've just been thinking about classical atoms or classical ions. The very last thing I want to discuss is the quantum mechanical case. Which is just like the diatomic case. In that the energy of the lattice vibration in the nth energy level is given by E sub n, which is n plus a half h bar omega. But now our omega is Q dependent. So it's in the nth energy level at wave vector Q. And so for a particular value of Q, say this point here, we'd have a particular value of omega, and then the allowed energies are given by n plus a half h bar times whatever the omega is at that Q. And the term phonon, often we use the term phonon really interchangeably with the term lattice vibration. A phonon is really a quantized lattice vibration. And the quantum of vibrational energy which is needed to move the lattice between two vibrational energy levels. This is just h bar omega q. This is formally what we call a phonon. So that's all for today, and thanks for listening.